record. Now camera is on. Well, a more realistic situation describing the vitrification is that minerals like, for example, calcium carbonate, they are surrounded by air that contains appreciable amounts of carbon dioxide, or in the worst case, other stronger acids also, like sulfur oxides and such. But suppose if a start is to check for calcium carbonate in equilibrium with carbon dioxide. What we know is that calcium carbonate produces, together with some carbonic acid, we can assume that it is forming calcium ions and hydrogen carbonate. Or if we go for this previous simpler version, calcium carbonate produce calcium ions and carbonate ions. So we know that carbonate ions and carbonic acid, they produce something like hydrogen carbonate. Let's see if we can find anything. And this is perhaps a horrendous picture, but it's not so dangerous as it looks like. First, we start with the calcium carbonate. Just the traditional naive version. And then what to do? Carbonate ions, where do they come from? Well, they come from hydrolysis of carbonic acid that comes from reaction with water of carbon dioxide. Carbonic acid produces is dissociated into hydrogen ions and hydrogen carbonate. Maybe down here we should try to get rid of the reaction with water and carbon dioxide surrounding. What about this one? Is it stable or not? Well, we find it in some formulas. Sorry. We find it here. For example, the inverse reaction of dissociation of hydrogen carbonate to carbonate and H+. Since it is the inverse, it has it's the reverse reaction, then it's the equilibrium constant is the inverse. Then we get hydrogen carbonate, but H+, yeah, carbonic acid is perhaps a possibility, but where do we get that from? We get it from reaction with carbon dioxide and water, and carbon dioxide aqueous we get from dissolution of gaseous carbon dioxide. Here I said that K3 is approximately 1. This is the only strange thing here. But mainly carbonic acid is composed of, if we say that this is in addition similar to carbonic acid, so then one could put this star on it maybe. Then it's approximately equal things on both sides. They are present. Perhaps it should be some other value.
But is it 1 because all of the carbon dioxide turns into?
Yeah, that is a good argument, because if this carbonic acid is consumed, then this one will also be consumed, or perhaps it, I mean, it could perhaps be some other value, 10, but that will only make a a constant difference at least. Maybe 1 is an underestimate. But if we take all of these, carbonate, we find it here. Hydrogen carbonate, hydrogen ions. Well, we don't want hydrogen ions, but those we can put towards that one. Carbonic acid, we don't want that either, but we only want the effect from carbonic acid from Aqueous, that one. Now, what's left here is described by this equation down here. Since we composed it of 5 different equations or equilibria, the equilibrium constant is the product of these 5 individual equilibrium constant. It's not necessarily so that this is the only way of arriving. The final result here is quite reasonable. Calcium carbonate and carbon dioxide from the atmosphere in a wet environment forms calcium ion and hydrogen carbonates. This is a good approximation for what happens to calcium carbonate that is affected by rain and saturated carbon dioxide. One can perhaps construct it slightly different. Here is another version with 6 different reactions. What the difference is that the final result is the same, and one can't say that one of them is better than the other. But what did I use? I dissolved carbon dioxide, and that is transformed to carbonic acid, and carbonic acids dissociate. But here I let the up here I did let the carbon dioxide carbonate ions react with hydrogen ions to form hydrogen carbonate. Then I identified that reaction as the inverse of the second dissociation of carbonic acid. But I can also let carbonate act as a base with water, forming hydrogen carbonate and hydroxide ions. Then I introduced hydroxide ions, but those could be we could get rid of by adding the inverse of the water out of proteolysis. So the result is the same, but constructed slightly different, and the equilibrium constant should, of course, be also the same. Where is the calculation of the equilibrium constant? I didn't include that. It is hopefully included in the text. These figures are from the compendium KZ 4007, and this is probably the chapter 6 concerning carbon dioxide. Maybe that is major chapter in that text. I think the K is 1 times 10 to the minus 6. The product of all these individual Ks should be something like that. So let's put up the expression. We start with pure calcium carbonate and carbon dioxide. Here we give the activity of carbon dioxide. Since it is a gas, it is the pressure measured in atmospheres. So one can put it in something like 400 ppm is 0.0004 ppm, and that is a problem. That is parts per million, weight by weight. So it's actually 400. If you take a kilogram of air, you have 400 million parts per million of that is carbon dioxide. And since air on average and carbon dioxide don't have the same molar mass, this is not entirely correct, but it's, if we assume what is the molar mass of carbon dioxide is 12 plus 32, that is 44, yes. And air, what is that? It's something like 29 gram per mole. I mean, nitrogen is 28 and oxygen is 32, and this is 80% approximately and 20% oxygen. So the average value will be somewhere close to 29. Then whether is 29 and 44 nearly equal? If you are that liberal that you can answer yes to that question, then you don't need to change that 4. But if not, maybe it should be a 3 is a better approximation, or even a second decimal here. But I mean, in principle, it doesn't do a large change. Activity of water is, as usual, 1. Producing from the initially nothing, but at equilibrium, we will have X moles per cubic decimeter of calcium ions. And since we have nothing else produced as counter ions, we need to have 2X. I mean, that is the stoichiometric coefficients here, 1 to 2. And then it's not so difficult anymore. It's just the product of these two. 4x3, how do I arrive to that? Well, if this is x, and we should have 2x, but there is also the 2 occurs 2 times. This is sometimes a problem seeing, but believe me, it should be like that. Yeah, maybe one should instead of typing it as HCO3 minus times a square, if we say it is 2x, it's 2 times. So instead of that 2, you write, so this is also 2x. This is a symbolic concentration at equilibrium of the hydrogen carbonate. But instead of writing everything literally, explicitly like that, we usually say a factor of 2 here. And that is the reason why the 2 comes in 2 times in the expression for the equilibrium constant. So it will be 4x3, and the denominator, calcium carbonate, is unit, water is unit, but the carbon dioxide is considerably smaller, something like that. And then we can solve for x equals 4.7 times 10 to the minus 4. Maybe we forgot what x was, and what we actually sorry, this X is sort of calcium ion concentration, 4.8 or 5 times 10 to the minus 4, compared to only hydrolysis with water that was 9 times 10 to the minus 5. It's considerably less compared to the situation of no hydrolysis. It's 5.8 times 10 to the minus 5, even less. So one can draw the conclusion that allowing calcium carbonate to react with carbon dioxide increases the solubility a factor of 10 nearly, compared to the situation where we don't have any reactions with acid. Well, carbon dioxide from the atmosphere and water. This is quite a realistic value. Don't trust the decimals, but it's somewhere in the order of this, plus minus 50 or 100% maybe, in reality. So, what we have been doing now is to, well, we have been looking at natural waters and acid bases, and some solubility discussions, including gases and solids, solubility of solids, I suppose, but you can also speak about solubility of gases. This is traditional, in a way, acid-base chemistry. Sometimes the equilibria that you need to formulate are rather complicated, so it is useful to have graphical methods to get a better overview. These distribution diagram and or PHPC diagrams, preferably constructed with some computer programs. You don't need to struggle with that. But apart from acid bases, we also have redox. This is what we should discuss slightly more. Redox equilibria, and when we combine the redox equilibria with acid-base equilibria, there will be new kind of distribution diagrams that we gave. There was a guy called Marcel Pourbet that published them for some 50 years ago or something like that. So thus we call them Pourbet diagram. They include both. They are maps over elements and compounds, both in terms of acid-base environment and redox environment. These two are called master variables of the surroundings. Two important determining factors how chemical elements react and in what form they will stay, so to say. Also possible to calculate with Medusa. And for example, I mean, we could have only acid-base equilibria. Here is carbon dioxide in atmosphere or in water, various forms of carbon dioxide. We call them other stuff. We call them carbonic acid and carbonate ions and such things. Or they can react with, some of these species can react with metal ions and form solid materials. But in principle, this is acid-base reactions and dissolution. Maybe one shouldn't say that this is acid-base unless you claim that carbon dioxide molecule is an acid and the water molecule is a base. Then you can fit it into acid-base nomenclature again. But usually try to well, we have a dissolution reaction, precipitation reactions, a lot of different groups, categories of reactions, and we don't only speak about acid-base reactions, which is perhaps good, but there are no sharp borders between the concepts. Finding what kind of what kind of form that carbon dioxide exists in. Is it carbonic acid or is it carbonate ion or something like that? That is sometimes called speciation, determining what type of species are present. And for example, we need pKa values if it's acid base, and maybe some logarithmic diagrams or fraction diagrams. We can see here is a typical fraction diagram. We have been looking at it before, where we, if the goal is to check and determine how much of the carbon dioxide exists as carbonic acid, the red one at a certain pH, well, then it's okay up to pH 8 or something like that. If we need to know carbonic acid at pH 12, this diagram is useless. Then we need a logarithmic diagram, which extends the different species to very many orders of magnitude. This is otherwise we need to remember other ions in natural waters. It's not only carbonates and hydrogen carbonate. This is only hydrogen carbonate. This is the major negative ion in freshwater, natural waters. Otherwise, also some sulfate ions. And where do they come from? I don't know. But they are present more or less everywhere, in less amounts than hydrogen carbonate. And chloride ions are hardly present at all in freshwater. Oh, sorry. Athena disconnects me. It doesn't like this. No. Sustainable here, environmental, yes. In freshwater, hydrogen carbonate and sulfate ions are the major negative species, but a slight amount of chloride ions. But in the sea, chloride ions dominate actually. But they do not have any acid-base properties to speak about. They do have, but very, very, very weak base. Other negative ions that are present in minute amounts are fluoride, nitrate, and phosphates. Depending on the pH, the phosphate is not occurring as phosphate, very often not, but all of the different protonated phosphate ions should be represented by this one. None of these is particularly dangerous. I mean, you shouldn't eat a lot of nitrate ions, but if you eat ham, for example, then you get in some nitrate and nitrite also, NO2 minus. And if you brush your teeth with the toothpaste containing fluoride ions, you will add some fluoride ions to your body liquids, but it's not a lot. And that amount is actually healthy for your teeth. Positive ions, they are calcium, magnesium, mainly from vitrification of calcium carbonate or calcium or magnesium containing minerals in fresh water. But in the sea, the main positive ions is sodium chloride. It's nearly 3%, or actually slightly more than 3%, 3% of sodium chloride in the sea. So it's something like 0.6 moles per cubic decimeter. It's an enormous amount of sodium chloride in the seawater. So we're not using it very much in some industries. Industries producing chlorine gas and sodium hydroxide, they use seawater. But there is more or less an infinite amount of sodium chloride in the seas. Some potassium, but not a lot. And maybe some ammonium ions, but not a lot. Ammonium and nitrate, they should. Those are fertilizers, and also phosphate. So these free ions shouldn't be present in natural waters. All of these have some kind of acid-base properties and also redox properties. So they are the objects for speciation. Perhaps one needs to draw these kind of diagrams in order to determine what kind of species are occurring. I think that was the last.
Can I just ask, so
Yeah,
in water,
yeah,
I reckon you can form sodium carbonate.
Yes.
And does that have any function like calcium carbonate? No, it doesn't work.
Yeah, that is actually a question in one of the calculation exercises in number 2. Sodium carbonate or calcium carbonate, what is the difference between those two? Yeah, it's actually solubility. The calcium carbonate, it's 2+ and 2- in the carbonate ion, so there's quite high attraction between them. So they tend to precipitate unless it's an acidus or neutral or acidus, where the carbonate ions, they decompose them. But sodium is only 1+. And if you take a bottle of sodium carbonate and try to dissolve it in water, it's very soluble actually. It seems to be enough with this difference between sodium plus and calcium 2+ to make sodium carbonate considerably more soluble than calcium carbonate. A bit strange, but I mean, at least the trend fits. And sodium and chlorine is very soluble, but approximately as sodium carbonate. So it's not possible to do fine details using this crude rule that high charge on positive ion and high charge on negative ion produce insoluble compound. This is true for maybe calcium and carbonate, and especially for aluminum 3+, and for example phosphate 3-. Calcium phosphate, this is approximately the teeth mineral that occurs in bone and teeth. So this is very insoluble, which is good. I mean, you can drink water without fear that your teeth will dissolve, but don't try to drink hydrochloric acid, because then you will unfortunately suffer from dissolution of your teeth. You can do the experiment if you have a if you save your old teeth when they fall out as a child, or if you broke a teeth or something like that, or if you happen to have a bone, piece of bone, put it in some acid environment and it will dissolve. This is quite, if you eat chicken, for example, then you can take a bone from a chicken, which is quite strong and sturdy when it's fresh. After a day in hydrochloric acid or say acetic acid is also kind of okay. And then you dissolve all the mineral content of the bone and only have the organic ligament. What is it? It's a protein called collagen mainly, and that is formed. Then it the bone is something like rubber or something like that. That is perhaps an experiment we should do as a part of this course.
So that the sodium carbonate and calcium carbonate, there is a difference in solubility.
Yeah.
And that is because the charge of the...
Yeah, that is a simple model. I mean, calcium 2 plus and carbonate 2 minus is a large attraction between these two, but sodium and carbonate, it's less attraction because the attraction is some the force is proportional to some constant, and the different charges like that.
Right, I remember this equation.
Yeah.
So phosphate. Oh, sorry.
Yeah.
Sorry.
Yeah.
Phosphate, like any iron bond with phosphate, is like not that soluble at all. Then the aqueous.
Well, yeah, that is reasonable. Unfortunately, sodium phosphate is very, very soluble. But magnesium phosphate, this is quite a strong bond. Here indicated by a solid line. It's not a traditional covalent bond, even though it may have some covalent character, of course.
Aluminum.
But aluminum, that is very, very strong bond.
Okay.
But all of these, I mean, the H plus, it's only a single valued cation, but can it conquer aluminum 3 plus? Yes, actually. This is a stronger acid than any of these two, 3. So it will easily attack the phosphate and then dissolve this compound. So most of the sodium plus and chloride minus, single plus and single minus, such compounds, they are soluble in water. Unless you remember silver chloride. This is silver and sodium. They are quite similar in size and charge, everything. But silver chloride forms a very strong bond. Sodium chloride also. I mean, if you look at melting point of these compounds, the melting point of sodium chloride is something like 800 degrees Celsius. So I think the melting point of silver chloride is actually less. It's not very small, but meaning that bonds should be slightly weaker in silver chloride than sodium chloride. But on the other hand, this is producing very strong bonds that is not possible to replace with the bonds to water molecules. But with sodium, it is. There is an extension of the acid-base theory called the hard and soft acid base theory, but we deal only with soluble compounds and insoluble compounds. It's enough to look at them as a first guess, at least. If there is large charges of both cation and anion, then it forms an insoluble compound. The hard and soft acid base theory take into account ionic and covalent interactions also. But we need to delimit discussion. Yeah, more questions before we start with lecture 2 that we should have started already? This is perhaps the same picture as previous. So concerning carbon dioxide, we have been only discussing acid base and solubilities from carbonates and such things. But now we should also introduce some redox properties. This is perhaps of interest. There is, of course, I mean, water and carbon, hardly any redox discussions deals with water and carbon, or we don't need the redox properties because reducing water or oxidizing water is possible. Yes, it's possible to oxidize the oxygen in water, thus liberating oxygen gas, and it's possible to reduce the hydrogen in water, liberating hydrogen gas, but it's not common. You need to you need a laboratory or some device, electrical device, for actually doing it. Carbon dioxide is very stable, and I mean, the plants, vegetation, they can reduce the carbon 4+, the formal carbon 4+ in carbon dioxide to carbon 0 approximately in organic compound. It was a space in between in and organic there. Making, for example, hydrocarbons, carbohydrates, I mean, that is food. They do that by utilizing the energy in the sunlight. Plants that you turn into a dark closet or something like that, they will die after a while because they can't synthesize. Even if you breathe at them, they need light, otherwise they won't survive. Well, if you feed them with sugar, then maybe they survive, but they will be very, they won't contribute to the food on their own, at least. So, well, there are sources and drains of both hydrogen ions, and what about the redox? Then the sources and drains of electrons, maybe. That is an easy way to address all different redox equilibria. We can go to look at equilibria with thermodynamics. This is quite easy, although if there are a lot of hindrance, for example, kinetic hindrance to thermodynamics, perhaps we won't have equilibrium situation. So it's not useful always. It is useful for looking at water and carbon dioxide. but not necessarily in all respects. Kinetics could be difficult. It is good that kinetics is difficult because humans, for example, they are composed of carbon 0 approximately, organic compounds containing low valent carbon. And we are not stable in an atmosphere of oxygen, but should essentially transform into carbon dioxide. This is no fun, I think. It's enough to breathe. There is a lot, there are a lot of circulations of different materials. For example, water. Here is a figure from an old book that water evaporate from lakes and oceans and precipitate also. And then if it comes into atmosphere, then it can precipitate over land and add to that vegetation can grow. But we don't need to deal with this. The figures here are actually in cubic kilometer, so it's quite a lot. Let's dwell into dissolution of some important substances. For example, oxygen gas is possible to dissolve in water to get an aqueous solution of oxygen. Whether it is a dissolution or if it's a reaction with the solvent is an open question in a way. Is the left-hand side here, is it the same compound as the right-hand side? Well, if you answer yes, then you mean that the oxygen molecule in the gas, well, it's isolated from, it's quite large distance to neighbors. And it's also kind of large distance to neighbors in an aqueous solution. But on the other hand, it's considerably less distance to neighbors in an aqueous solution between oxygen gas molecule and water molecules in the surrounding here than it is in the gas. I mean, the distance between oxygen gas molecules in the gas phase could be, say, 10 or 100 diameters of the oxygen gas molecule. So they are literally on their own, each one of them in a gas phase, but not in an aqueous solution. And that is perhaps a reason to say that this is slightly different. There are some bonds here between chemical bonds between the oxygen gas molecule and the solvent, or unless you want to speak about bonds, maybe they are not strong, not at all, but they are stronger than not at all. Sorry. There are very, very weak bonds between the oxygen gas molecule and the solvent. And they are stronger than zero, so to say. There is an equilibrium constant where one can measure the concentration or the activity of oxygen gas in the solute and the activity of the oxygen gas in the gas phase. Activities of solutions are usually termed by the value of the concentration, and activities of gases are usually termed by the pressure measured in atmospheres or possibly bars. Atmosphere and bar, it's approximately the same unit. It differs by 1% approximately. So don't use Pascal here. because then you would get the pressure of oxygen in the surrounding is approximately 0.2 atmospheres, or 20,000 Pascal. And 0.2 is a bad approximation to 20,000. But if you use it in atmosphere, then you will fit the correct value of the equilibrium constant. This capital H here stands for Henry. That was some guy making a lot of job on soluble compounds, especially I think he started with gases and distillation and such things. Now let's see. Time is running. It's 10:47. Is that true? Time runs when you have fun. Is it time for a break again? I think so.